what we can predict just on this condition, whether it's going to deposit on the wall or not. Either of those two particles. By the way, let's call this equation that we had derived as equation G, which I'm going to call up later on. Okay, so now I'm trying to figure out the different parameters that appear on the left hand side of this inequality. So V fluid is given to us. The rho P, we are assuming water-based aerosols or droplets. The slip correction factor is 2.7 for the smaller particle, 1 for the larger one. And we need the C in the particle relaxation time. So let's evaluate that now. So tau is rho P d squared Cc over 18 mu. So this is equal to 1000 is the density times 0.1 is the first particle size micron, 2.7 is its slip correction factor divided by 18, and 1.8 10 to the power of minus 5 kg per meter second is the value that we have been using for new air is the viscosity coefficient, and this is for 0.1 micron, and then we have 1000 times 100 10 to the power of minus 6 square. The correction factor is 1 now and 1.8 times 10 to the power of minus 5. Can you give me these two numbers? 8.3 into 10 to the power of minus 8.3 into 10 to the power of minus 8. So, yes. So I have 8 times 10 to the power of minus 8. Let's just use that. What's the second one? 0.0308, yeah. So I have 0.031. Okay, so what else do we need? So again, we are trying to use this criterion G. We have evaluated the tau in OV fluid. We don't know what is L0. We don't know what is L. So let's think on those. So what is L0? So if you think about the geometry over here, L0 is basically the radius of curvature of the tract, right? Now, based on the array that you are trying to apply this technique to, you can figure out the main radius of curvature. That's up to you. Typically, what I've assumed is coming from some very rough estimates. So the value that I'm going to use here is L0 to be 5 centimeters, which looks like a fairly reasonable estimate here, because if this is being approximated as a circle, that being the radius as 5 centimeters, it seems reasonable to me. But precisely, you can probably take something which is closer to whatever the actual value is. And this by itself would be another new line of research. You can get a new anatomic geometry, which we have a lot of in our lab. You can develop the surface curves that delineate this space, and then you can figure out what is the mean radius of curvature and apply that. And I'm sure no one has done anything like that before. Even in the paper that I showed you, he did not get into the anatomically realistic geometries. For now, let's assume that L0 is 5 centimeters. So 0.005 meter, and L is the radius, right? I have used 0.05, but the thing is, let's quickly take a look at what a possible radius could be. So in this particular 3D print, the reason why I had printed this was I was trying to track drug delivery to this region over here. What is this region? From what we learned this morning, it is where the larynx is. So after the constriction, so we are trying to send drugs to some granulomas, some tumors that are formed in this region. So this is a cross section at the larynx. On the other hand, if you think about the other geometry that I was sharing with you guys, so this is what the slit cross section is. Now, if you ignore the thin regions at the top, if you just focus on the thicker parts, what the corresponding radius will be, that is up to you. You can measure it and you can make it as accurate as possible. Maybe think of it as the hydraulic diameter of hydraulic radius of this region, figure out how much is the dominantly weighted region, and then figure out the radius from there. For this particular problem in class, I'm going to use some approximate values. But again, I'm going to reiterate that these are research questions and you can use the precise values and that itself can lead to a new line of work. Okay, so the value that I have used is 5 centi, 0.5 centimeters, yeah. So yeah, this one was wrong, right? This is 0.05. So L0 is 0.05, 1 or a smaller, I have used 0.005 meters as the radius. So let's see what we get with this values that are probably close to what is reality, but still are not very accurate. Now, before we go into MATLAB, let's quickly figure out this factor that we saw appearing in equation G. So this factor tau v fluid square over L naught. So how much is that? So tau v fluid square over L naught is, you have the taus and the v fluids over here. Can you give me the corresponding numbers for d is equal to zero point 0.1 micron and d is equal to 100 micron? So for t is equal to 0 0.1 micron, 4 into 10 to the power of minus 5, yes. What's the second one? 15.5. 15.5, yes. So now we have all the values that we are going to need. So let me write down the problem statement. So thus the formalism in G, which is that equation, that inequation, the inequality that we have derived, in G could be simplistically written as the cofactor. I'm just going to, in the code, you will see that I'm just using the alphabet A. T plus, I think I'm using B for this, e to the power of minus t over tau. Tau is B minus 1 minus L is 0. So basically, A is that tau Vf square over that factor, and B is tau Vf. And I brought L to this side. So what I'm going to do is find the numerical solutions that would put the particle at the wall. And what would be, so if I solve for this, A has a numerical value now, B has a numerical value, L has a numerical value. So the only unknown in this equation is this small t, time. So I'm going to figure out what is the time t for the particle. The first case, the particle 0.1 micron, and in the second case, the 100 micron particle. How long does it take for the particle to reach the wall? Does the argument make sense? So from inequality, we have now moved to an equality condition. Okay. So where t is to be solved, to figure out the approximate delta t until the particle or for the particle to deposit on the upper airway wall. We need to be cognizant of the fact that we are still talking about the upper wall as such, because that's what the function was, to pick up the position of the lower wall because it changed. We have to change that equation. If we have time, we can take a look at that as well. So that's not what was done. It's just looking at the upper wall. Okay, so we are going to do this derivation. So this is now the problem statement. Do this derivation for d is equal to 0.1 and 100 micron. For the numerical solution, you may use the provided MATLAB code. So one thing that I'm trying to be curious about and something that I haven't done yet is, what if we do pick the lower wall deposition? What changes in that criteria? Can you guys look back at your equation and tell me what is the precise thing that will change if instead of the upper wall deposition, we rather try to crack the condition for a lower wall deposition? So this is where I was discussing this, right? So we got this G, and the conditions for upper versus lower wall depositions are up there. So our T greater than L0 plus L is upper deposition, and L0 minus L is lower deposition. So as a result, when we are using this criteria, and from this inequality, when we move to the inequality, we took L to the other side and it became a minus L. That minus L would be plus L. We rather try to try the lower wall deposition. So I haven't tested the code for that yet. I don't know if it would work, but we can try it out. But the thing that I think should work is the upper deposition. So let's try that. The reason why I'm unsure whether the other one would work is because we have to set up some initial trial values in the code, and that dictates whether it manages to solve for it or not. Okay, so let's now go to MATLAB. So by the way, again, if you go to our cloud folder, the MATLAB codes are under the folder called MATLAB codes. So you can use them directly from there. Do I need to make a much bigger or is this fine? Okay, so This is for, let's first do the point, the smaller particle. So we have already derived the values for the different parametric values for that. So we have the A, which is the TVF square over L naught, to be 4 times 10 to the power of minus 5, right? So 4 times 10 to the power of minus 5. And the B, which is the tau, the relaxation time is 8 times 10 to the power of minus 8. Sorry, I am not really used to the keyboard of this computer. 8 times 10 to the power of minus 8. And L is SEM, which is 0.005 meters. And here I am trying to figure out the solution, but we do need to give an initial guess for the T. So let's see if this is the correct guess that would work for this particular example. So we know that this is a smaller particle, right? So it stays airborne longer. So the initial time estimate that I started out with is 100. So let's see what happens with this. So what we get here is the solution time for T is, the solution for T is 125. So that's more than 2 minutes. What do you think what happens to a particle if it stays airborne for 2 minutes inside the air? Would it deposit in the upper wall, upper airway? This particle is going to go downstream, downwind. If we do change this initial guess, let's make it smaller. What happens then? Let's make it 1. The solution doesn't converge, which is understandable because the solution cannot be anywhere close to that small value for the initial guess. On the other hand, if we do change it slightly higher, so let's make it 50, does it work then? It doesn't still. Let's make it 80. Now we again converge to that same value that we had before, 125. Now this is for the upper wall deposition. Now what do you think needs to be changed here for the lower wall deposition? The minus and plus on line 11. So this becomes plus. Let's see what happens if I run it. So we don't converge with this one. Let's start from smaller. Let's try 1 first for the initial guess. Still nothing, so let's go to 10. Still nothing. Let's go to 50, doesn't work. Let's go much bigger, 500. Nothing yet. Yeah, so I would leave this as an assignment for me and for you guys to see what happens if we do change that sign for L. And there is probably a reason why Sunny did not dare to get into that territory, and which we are missing maybe right now, but basically there is no reason why we cannot get that either. The only thing that I can think of is the typical trajectory of the particle, since we are not counting in gravity, it's basically almost impossible for the particle to fall back down moving to the straight lines. And that could be a reason probably there is no real solution for this particular condition. So we'll see with that. So that's a good question. Could there be a physical solution if it is indeed that?
I think it is a positive quantity over.
Right, right. So
That
if
is why
we,
it is not giving any.
this can never be equal to zero because and that's quite elegant in the sense that that particle can never go down as if there is no solution possible for this particle. We might have had something we were contemplating the gravity term, but here we are not doing that. So thanks for pointing that out, but yes, this is physically impossible. So we won't have the lower body position. So make a note of that where we did mention the lower body position. So let's change it back to minus L, but let me also make a comment over here. So this is where we derived equation G. So this would imply that tau Vf square over L naught plus T plus tau e to the power of minus T over tau minus 1 plus L will have a real solution for T, which cannot be true. So in this approach, we are not going to get the lower boundary position because both the terms are above this. Could this term become negative? So this term over here, this is e to the power of minus t over tau. So no, it can never be negative. So the lower wall deposition is not possible over here. Okay, let's move back to the code again. So I think I have corrected this. Let's run this again just to be sure. So 125. So now let's try out this was the smaller particle. Let's try out the bigger particle for which we have the parameters as A, which is tau, as 0.031, and sorry, A is not tau, A is tau Vf square over L naught. So that is, how much should A be for this one? You can look at your notes. 15.5. Tell me how much B should be for this one, which is tau 0.031, and the L is still same. Now this one, if I keep this same initial guess, let's see what happens then. We don't have a converged solution because this is a much bigger particle. It's not going to take that long of a delta t before hitting that condition over there. So let's make this smaller. Let's make it the initial guess to be 1. And we still don't get a converged solution, so we have to make it much smaller. Let's try the next smaller, the order, so 0.1. Still nothing. So let's make it one order smaller, 0.01. And now we have an answer, 0.0046 seconds. So that means this particle, the moment it is let into the air stress, it deposits within a fraction, within a very small fraction of a second. That means it is going to deposit in the upper airway. Yeah. So I don't think Sunny tracked this time interval down in its work in the paper. So feel free to get in touch with me if any of you here have interest in following up on this problem. Because physics is just time over there. And of course, I just like two particles of this, right? So you can develop a parametric, a best portrait by trying out this code and figuring out the deep critical needed for each such size. And then a nice study would be comparing this theoretical estimate with the corresponding safety generated estimate for a similar geometry. So if this interests you, let me know, and this could be a collaborative project for us. Any question?
And it is just like it's just starting time of 1 0 1 second after this is time to create the
Yes, yes. So it takes point zeros. So starting from the central point of the inlet cross section, it is supposed to take 0.0046 seconds to hit the wall. Given that is the flux that it is trying to move through, 5 meters per second. And the numbers are quick estimates, right? So we can make this biologically, physiologically more realistic. But this gives us the order of magnitude. Any questions? Okay, so let me note down some comments over here under each of these codes. Okay, so this is the one for t is equal to 0.1 micron. So this, the delta t being more than 2 minutes, implies that therefore there is barely any chance for upper airway deposition. And for zero point 0.1 micron, realistically, even while running series simulations, we don't see much upper airway deposition. So although I have kept the word barely, but it could be as good as there is no chance of upper airway deposition. On the other hand, if we had picked out something like, say, 1 micron or 5 micron, I don't go into that because we have to then again do the numbers for the tau and the cofactors. Then this word barely makes sense because some of them might still land in the upper area. Now, in the second case, when we have, and this to your point, like the size threshold analysis, we can do it this way as well. In the second case, when we had the D to be 100 micron,
just one thing.
yes.
Just making more. Because we have used this kind of large this bend we have used.
Yeah.
Can this maybe can it be sort of extrapolated in some way and branch somehow? Because it's just sitting there and then when branching also takes place, there is a chance that it can hit the center.
Yeah, so what he's assuming is basically if you think about the geometry here, he's talking about, well, he's not talking about that, but what I perceive is he was trying to do is one side of the area which is continuous going down. The theoretical model is not equipped to tackle any kind of branching in the cavity, because topologically that would be a very different from the other branch.
But if such kind of model can be made for a single branch, then it can be easily sort of scaled down to
Within the faculty.
all the branches.
Yeah. But it would be challenging in, I don't know the details yet because we have not done the work, but one thing that we do know, I need a chalk. I should not be moving this one. So let's keep it here. So if you think about uh, T junction, so this is just an extreme version of branching happening. So the flows come like this, right?
Maybe something like flow over a love body.
Flow over a block body.
Something
So
like that, not so dramatic.
you are suggesting what happens if
Circular.
so this is the bluff object and it goes like this. What happens then?
We have simplified 2D version because he has simplified it so much.
Yeah. Now I'm trying to figure out where you might encounter this. You
And this can be axisymmetric also. You can sort of make it axisymmetric and just do one thing.
so basically you're suggesting this region.
And this can be scaled down at every level because of sort of if we are assuming everything that then this can be a good assumption.
Now, one thing that people have definitely seen for a system like this, it is a very relevant system where if you look at the two sides of the nose, so think of this as the internal dividing wall on the two sides of the nose. This is called the septum. And then the two sides, I'm looking at my airway from the top down. The two sides converge together and then it goes further in. So the air comes in like this, but think about when acceleration occurs, that's exactly the situation that you are trying to describe. When the air,
Okay.
when the air is coming out. See, the thing is, when you describe it as an overtly simplified analytical model, I don't think I would agree with you on that. The reason being, we have to see this way that in terms of the details of the flow physics, the complex flow structures like the vortices, they are dominant mostly after the larynx in the tracheal region. The flow in the upper respiratory air space is fairly consistent in the sense that you can think of it as a pipe flow, which is basically what they're trying to do. If you think about this geometry that we use, there is no it's a pipe flow, right? But like in this code, we try to use the numbers instead from the anatomical geometry in terms of what is there, what is the radius of the cross section, etc. There is more than a simple analytical model that is using out all the details. It's not like that. But we cannot do this kind of modeling for the entire area, which you are in the right track that if we do encounter this kind of cloth body, you have to think about a different model technique. Maybe there is one, but and it cannot be something like this. Yeah. Question? Any other questions? Okay. So over here, let me write my only comment. So this is 0.0046 seconds. So this implies that there is prompt deposition. Therefore, a particle as large as 100 micrometer diameter would undergo prompt anterior deposition driven by inertia effects. And for that matter, when you are trying to approve this problem analytically, there is no other way out, right? Because you cannot really include all the details of the geometric topology into the problem. At best, what you can do is something like this. When you have a block body, and what I was trying to get at over here was this T junction is very useful because it's an engineering model, and we see this later on in the airway where things evolve like this, where you have sort of like a Y junction. So the T junction is an extreme version of this Y junction, and this again goes to further Y junctions as we go further downwind in the runs. Now, what people have seen is in flows like this, there are vortex tubes that are formed in this region that can trap the particles. It's very unexpected. If you think about the streamlines, this vortices should not be there, but they are there. And question is whether these vortices are relevant for the Y sections over here. So there is more going on. There is some more going on in my group as well, where we are trying to focus on this kind of T junctions and coordinate our understanding, make it sort of like a
I
canonical
think
model.
this was something like Howard's own group was doing it.
Yeah, Howard has done this. I think Garrett McAndrew has done something as well, and they have collaborated together. And I think 3 4 years back at one of the DFE meetings, Howard posed this as an open question in the sense that they have just looked at this one. Uh, Frankly, there is no explanation why the voice should be there because the streamlines they should drive this right? But no one else has really done this experimentally. What I have done is there is an archive preprint which you can find from my website where we did show that computationally it is there. Those vortex fields are there. And the question is what particles get trapped over here? What Stone is learning, these are the particles with density lower than the density of the element, which is entirely against what we have been doing since yesterday. But if you think about the infection transmission application, that maybe virus nuclei is the particle that you're trying to track, then those get trapped in this kind of body still. And Gareth McAndrew, he has also done some simulations on this. Okay, so any other questions?
Zero level.
No, it could be turbulent. But there is a certain range of Reynolds numbers over which this tubes come up and then they vanish. So it's sort of like yeah. So it's
Some sort of localized switching application.
exactly. So it's a sensitivity study as well. And Howardstone wrote 2 papers back in 2014-17. It's an interesting problem. But that is a T junction, and whether this could be correlated to Y, and for that matter, I have a picture which I think is there in my research talk where I actually found out a T junction not in the downwind tract, but I don't have that 3D model here. But if you think about the geometry further downwind, and if you think about a cross section over here, there are some T junctions there as well. In fact, in the upper respiratory areas, because of something called the turbinates. Do you guys know about turbinates? These are the So overhanging ledges from the lateral wall of the nucleus that make this kind of angles. And some of them they do look like the young white angles. Okay, so let's move on. So until now, what we have been doing since yesterday was just the particle transport, right? So we developed equations for a single particle moving through fluid. Yesterday, we kept on using that equation after the first half today, and then we tried to use that equation within a geometry that sort of resembles a respiratory tract. Use of that geometry gave us the initial conditions, the geometric conditions, which helped us to solve the differential equations. That's where we are at. But we have been just thinking about particle transport. We have not really commented much on the fluid dynamics. We have not really thought much about the flow physics. And that's where we are going to move to. We are moving away from particles for a while. So fluid dynamics in the respiratory tract. So basically, certain elements that we have discussed since yesterday, there is of course how the particle reacts with the flow, interacts with the flow in terms of its sizes and where they might land. That is important because the flow features that are formed in the fluid field, they are really strong enough to induce particles of certain sizes. So the vortices that we want in the flow field probably cannot impact the particle much if its inertial component in its motion is already strong enough. So while trying to understand the flow features, we also need to think about whether they can impact the local particle transport. So let me write down some comments first before we go further in, and we are going to use some equations and try to create some plots to figure out what are the components in the fundamental Navier-Stokes equation for the flow field could be relevant in terms of our understanding of the problem. And based on whether we are trying to look at the upper respiratory tract versus the thinner bronchial channels, different terms could be relevant on the Navier-Stokes equation. So, to answer questions, on the fate of inhaled particulates, that is aerosols with d less than 5 micron, or droplets with d greater than equal to 5 micron, it is necessary to understand the fluid motion inside the respiratory tract. Now, while trying to understand the fluid motion inside the respiratory tract, the approach that we took with the analytical formalism for the particle transport might not be a very valid approach, where we idealize the geometry and then we try to get a generic trend on the particle evolution regions. Here we are talking about the flow field moving through this complex geometry. So the moment we start to simplify this geometry, we are going to lose those flow fields, right? So to give you an example, oops. To give you an example, when you have, let's assume you have a very complex geometry like this. let's assume that this is the inlet and this is the outlet. So going by the kind of simplification that we have been using until now, that we try to sort of keep the topological nature of the geometry intact, and we assume that there is a geometry that is an equivalent geometry that goes like this, and maybe even diverge out a little bit to get the bigger cross section. And the claim was this two are equivalent. That's essentially what we have been trying to do until now. But now think about the flow field over here. The streamlines that go in to here might be creating some kind of recirculating flow that can lead to some vortex regions over here and maybe over here. But this is a simple pipe flow. Do you expect that similar flow field features will be there? You know, there is a smooth surface or smooth wall. So that approach of simplifying the geometry and then applying our theoretical weapons won't hold ground anymore. So let's keep that in mind. And we should be thankful for that because then we won't know anything about what is going on across different subjects. Because as I think I was pointing out yesterday that all our anatomical geometries are different. In fact, the left side of my nose is different to the right side of my nose. So to figure out these differences or to make or to develop some work that can directly impact a particular person or a group of individuals, we should be thankful that the flow field does react to the geometry. It's a geometry coupled system. So we should keep that in mind before trying to develop any kind of reduced order framework for this. Okay. So the flow physics within the respiratory airspace is a function of the anatomical geometry and the details and the geometric details can and do impact or do vary from person to person. Having said that, we will see, I think, tomorrow or day after tomorrow that laryngeal constriction, the constriction that happens right before the larynx, is sort of similar across subjects. So how much it diverges, how much it converges and then diverges is similar. So that vortex formation, the strong vortex formation is fairly consistent across all subjects. The precise strength of the vortex might change a little bit, the location might change very little bit, but it is there. That is the general shape of the anatomy, which is true for any subject. Okay, so keeping this caveat in mind, we can still try to derive some general description of the flow of the fluid dynamics inside the respiratory tract. How do you think we can achieve that? We cannot idealize the geometry as we saw from there. What we can still do is use Navier-Stokes, try to non-dimensionalize it, figure out what could be the dominant terms, right? So we do know that the flow is of a certain kind in the upper respiratory tract compared to when it is in the alveolar channels. So based on the difference in how the flow is, how fast it is, how slow it is, whether it is unsteady, whether it is turbulent, whether it is laminar, as most of us as mechanicians over here, we can ignore certain terms in the media flows. And that can help us develop a broad understanding of what might be happening in the upper respiratory areas versus in the high generation vascular channels. So that's where the approach is going. But before we go in that direction, the fundamental approximation or assumption that goes into the flow field is the fluid domain incompressible? And frankly, I never really thought about this question. I just assumed that it is incompressible. Is it okay to just assume it is incompressible for this kind of airflow? The Mach number dependence is less than 0.3. What are the different conditions for that? One is the temperature gradient difference. And that is the only thing that did not seem obvious to me because we are breathing in air. Forget about low. If you come to where I am coming from right now, it is minus 32 degrees Celsius. That's what my wife told me right now. So they have delayed school start by 2 hours in the morning today. So minus 32 degrees Celsius, you are breathing in that air. Our tissues are at a certain temperature inside the body. That was one thing that I was concerned about whether the temperature difference can sort of play against our incompressibility function. But thankfully it does not. So that is one thing. The other factors are, so for example, the flow rate, it does not exceed to that kind of level, of course. And in terms of the density, it seems like some folks from the medical community they tried to argue that maybe that is not reasonable to assume that it is incompressible, but then the air that we are breathing is mostly what? 3/4 of it is what is air balloon? Yeah, before. So basically the components that get exchanged through the gaseous respiratory exchange process in the alveolar sacs, it's just a very tiny component of it. It does not really change the density much. We can definitely assume that the air has constant density going in, but I'm not talking about what is going on in the exchange between the pulmonary channels and the alveolar channels. And still, because the component that gets exchanged is such a tiny fraction of the air, the density doesn't really change much. But these are not these two, at least the density part and the delta T, the delta time, the delta temperature, they are not really obvious. And
So what really happens? Like we are basically getting the air at minus 32,
yeah,
and as soon as it enters through the nasal pathways, it achieves kind of 37 degrees Celsius around.
the thing is, I have written a couple of papers on this. So basically, people or animals who live in cold climates, their nasal passage is much, much more tortuous. So it's like this. So as a result, the air gets warmed up very early. As human beings, our nasal passage is still tortuous as we know, but not as tortuous as say some of the mammals that live in this very cold regions. So as a result, we are not supposed to breathe in air outside that kind of thing. But it's a we actually in 2020 we had got a grant from the NSF just on this application that this tortuous nasal passage could it serve as sort of like a biorespiration to warm up fluids or to screen particles that are embedded in the fluid. And we actually developed a mask filter design using bio-inspired respiratory tract geometries for the filter channels. Okay, so is the fluid domain incompressible? Yes, it is incompressible, but let me write down the points over here. So a pure fluid flow can be considered incompressible if the Mach number is less than zero point 0.3. Now, that is true if the delta T is less than 30 Kelvin and the V flow is less than 100 meters per second, both of which are reasonably true in our case. Now the other effect is about the density. So how good is the constant density assumption? So as Dr. Shamoto pointed out, nitrogen is the primary dominant component in inhaled air, around 3/4. So nitrogen comprises more than 3/4 of the inhaled air. 3/4 of the inhaled air density, and is not exchanged across the airway tissues and lung epithelium. So if that is the case, the compounds that, as I said, that are exchanged, they don't really change the density much. So the variations in the other inhaled gaseous components like O2 and CO2 do not significantly alter the density of inhaled air. But this approach by itself, if you think about some ulterior applications where think about the World War II gas chambers. These assumptions might not be true then, because the air that was going to be inhaled probably had some very different constitution, the compound fractions, and the way the gaseous exchange happens at the final generations of the quantum branching would have been messed up. So something to think about, and it could lead to other academic research as well. Okay, so with this being true, incompressible, thankfully now we can use the Navier-Stokes equation that we all love in its incompressible format, which oftentimes, if I ask my students, my American students especially, after all the fluid mechanics, they can never write Navier-Stokes equation. And I tell them that once my advisor threw out, and this is a true story. So I come from a fluid mechanics group, of course. My advisor threw out a graduate student because he could not write Navier-Stokes after 3 years. So that was the reason why that person was thrown out. So if I'm the chair of the committee, but if I am the committee member, the PhD students committee whose research is supposed to be in fluid mechanics, that's the first question I ask. Right, the Navier-Stokes. If the person cannot, which they cannot sometimes, I tell them the story that you would have been thrown out of my research group, the group I am from. Anyways, I think let's wrap it up today. Tomorrow we are going to use the non-dimensional decomposable Navier-Stokes equation to say a few things. Before going into some more application-oriented problems, Dr. Shamuta is going to teach today tomorrow.
Also, there will be a change, like the top rate is the same.